All right, look up for a second. There's actually a pretty fascinating engineering mystery spinning right above your head. In today's explainer, we're going to decode exactly why everyday appliances, like that single-phase induction ceiling fan in your living room, absolutely desperately need this tiny hidden cylindrical component called a capacitor just to function. Seriously, if that little piece fails, the whole machine is basically a very heavy ceiling ornament. So let's dive right in and break down the hidden physics here, stepping through exactly what a capacitor does and why it's kind of the unsung hero of our modern electrical world.
Okay, to unravel this, we've got to get to the root of the problem with these everyday machines. Now, single-phase induction motors are everywhere, right? Mostly because they run perfectly on the standard electricity we already have piped into our homes. But they've got this one massive fundamental flaw. Unlike their heavy-duty industrial three-phase cousins, they just cannot start on their own. They aren't what engineers call self-starting motors. But why? I mean, what unseen force is holding them back from just spinning the exact second you flip the wall switch?
Well, the core issue is literally in the electrical current itself. Inside a single-phase motor, the alternating current creates a magnetic field. But because it relies on just a single phase of AC power, this magnetic field is constantly, and I mean constantly, fighting itself in a rapid loop. During the first half cycle of the alternating current, the magnetic field pushes the rotor in a clockwise direction. But then instantly, like mere milliseconds later in the second half cycle, it completely reverses and yanks the rotor counterclockwise. It's just an endless high-speed battle of push and pull. So what's the result of this fierce internal tug of war? A net starting torque of exactly zero. Zero! Think about it like this. If you try to push a heavy box perfectly equally from the left side and the right side at the exact same time, well, it's not going anywhere, is it? It'll just sit perfectly still under the pressure. And that is exactly what's happening to the internal rotor of your motor. It gets trapped in this totally useless state of humming and vibrating instead of, actually spinning. The energy is absolutely there, but the rotational direction cancels itself out completely.
Now that phenomenon we just talked about, that endless, frustrating push and pull, that's what we call an alternating magnetic field. It's a magnetic field that simply reverses its direction along a single axis, back and forth, back and forth. This alternating nature is the exact limitation holding the machine hostage. It's the whole reason the motor violently vibrates and buzzes but never actually manages to make that crucial first turn. It just completely lacks that sweeping rotational push you need to break out of inertia.
On the flip side, let's look at what we actually need to make this whole thing work. A rotating magnetic field. And this does exactly what it sounds like. Instead of just pulsing back and forth in a straight, linear line, the magnetic field actually rotates in a smooth, continuous circle around the stationary outer ring of the motor, the stator. This circular, sweeping motion is the absolutely critical ingredient to drag the rotor along with it, drive motion, and finally create that starting torque in an alternating current motor. So, here is the million-dollar problem-solving question for this explainer. How on earth do we force this conversion? How do we take a stubborn, back-and-forth alternating magnetic field and twist it into a smoothly rotating one? Well, here is the massive catch. The laws of physics strictly dictate that to naturally create a rotating magnetic field, you absolutely must have a minimum of 2 separate electrical phases. 3 works perfectly, but you need at least 2. But hey, remember the name of our motor? It's a single-phase motor. We are exactly 1 phase short of a solution here.
Enter the hero of our story, physically built right into the motor's internal anatomy, specifically a component called the auxiliary winding. Actually, if you've ever watched a tech repair a ceiling fan, you've probably heard them call this the starting winding. It's basically this extra coil of copper wire sitting right alongside the main winding, just waiting to be utilized. But if you just plug it in, it's still drawing from that exact same single phase of electricity from your wall, meaning on its own, it doesn't solve our problem at all.
All right, now this is where the magic happens. By taking our capacitor and wiring it directly in series with that auxiliary winding we just mentioned, we literally manipulate the physics of the electrical current. The capacitor naturally resists changes in voltage, right? And by doing so, we instantly create a crucial 90-degree electrical phase shift in the system. So now the current flowing through the starting winding peaks at a completely different time than the current flowing through the main winding. And you guys, this sets off just a beautiful mechanical chain reaction. Let's trace it. First, we add the capacitor to the auxiliary winding circuit. Second, that addition physically creates our 90-degree phase shift. Third, and this is the pure genius part, that phase shift effectively tricks the single-phase motor into developing 2 distinct phases internally. It's basically a counterfeit second phase. Fourth, With two phases now present and offset from each other, boom, we successfully generate that highly desired circular rotating magnetic field. And finally, step 5. That rotating field catches the rotor, and the motor just effortlessly spins to life. You know, understanding this precise mechanical chain reaction doesn't just satisfy your inner nerd. It gives you the ultimate, highly technical answer to what is widely considered a notoriously common engineering interview question. Seriously, whether you're an aspiring electrical engineer or just someone who loves pulling apart how the world works, if anyone ever asks you why we use a capacitor in a single-phase fan, you got the exact mechanism down. It's not just to give it a boost of power. It's to fundamentally shift the current, artificially forge a second electrical phase, and transform a buzzing, vibrating field into a rotating one.
As we wrap up this explainer, I want you to do something. Look up at your spinning ceiling fan, or maybe just listen to the hum of the compressor in your fridge, and ask yourself this. What other totally invisible physical forces are silently powering the devices you heavily rely on every single day? The next time you flip a switch, remember, you're not just turning on the power. You are literally bending the laws of physics. Makes you wonder what other secrets are hiding right there inside your walls, doesn't it?